Training a 13 billion parameter model used to mean renting a data center, but DeepSpeed makes it possible on your hardware for under $1,000 in used parts. Built by Microsoft, the tool doesn't shrink the model. It slices the memory it needs across your graphics cards, so nothing gets stuck holding a load it can't carry. Here's the number that stops people. A 13 billion parameter model, trained properly, needs 208 gigabytes of memory just for the training state. Not the activations, not your dataset, just the pieces the optimizer has to keep alive while the model learns. Where does that come from? When you train with mixed precision atom, the standard recipe for basically every serious model in machine learning right now, each parameter costs you 16 bytes. 2 bytes for the weight itself, 2 more for its gradient. Then 12 bytes the optimizer hoards in the background. A full precision master copy of the weight, plus atom's momentum and its variance. 16 bytes a parameter, times 13 billion parameters, and you land at 208 gigabytes. Now look at what you actually own. A used RTX 3090 holds 24 gigabytes of VRAM, so the model needs more than 8 times what a single top-end consumer card can carry, and that's before you count the activations. This is the wall. It's why so many people assume big training is a hyperscaler-only sport. The model doesn't fit, the run dies with CUDA out of memory, and the conversation ends there. DeepSpeed's whole move is to attack that 208 number without touching the model itself. Think about how normal multi-GPU training works. You take 2 cards, copy the entire model onto both, and each one chews through a different batch of data. It's called data parallelism, and it's simple. It's also wildly wasteful. Every GPU holds a complete, identical copy of all 208 gigabytes of state. 2 cards, same load, stored twice. DeepSpeed's Zero Redundancy Optimizer, ZeRO for short, looks at that and asks a blunt question. Why does each GPU hold the whole thing when there are 2 of them? Published by Microsoft Research in 2020, ZeRO's answer is to slice the training state into shards and hand each GPU only its slice. No device keeps a piece another device already has. That's the durable idea worth taking away, and it outlives any specific model generation. There's a difference between what the model needs to exist and what one single GPU has to hold at the same instant. Compression fights the first one and loses. ZeRO ignores the model's size entirely and just refuses to store the same byte twice. It ships in 3 stages, and each stage kills a different chunk of that waste. Let's walk them. Start with the biggest offender. Of those 16 bytes per parameter, 12 belong to the optimizer, the master weights, the momentum, the variance. That's 3/4 of your entire memory bill sitting in Atom's bookkeeping. Stage 1 partitions exactly that. Instead of every GPU keeping the full set of optimizer states, each one keeps only the states for its own shard of parameters. 2 GPUs, each holds half. 4 GPUs, each holds a quarter. The payoff, by Microsoft's own numbers, is a 4 times memory reduction. And here's the part that matters for throughput. It costs you nothing extra in communication. The GPUs already talk to each other exactly as much as plain data parallelism made them. You've cut your memory to a quarter and the network traffic didn't budge. That's free money, so stage 1 runs by default in most setups. But 3/4 of the bill was optimizer state. There's still the gradients and the weights. Stage 2 goes after the next piece. During training, every parameter produces a gradient, the signal that says which way to nudge the weight. In vanilla data parallelism, each GPU computes and stores gradients for the entire model. Then they get averaged together. Stage 2 says the same thing it said about the optimizer. You don't need the whole gradient set on every card. So it partitions the gradients along the same lines, each GPU responsible for its own slice. Stack that on top of stage 1, and Microsoft clocks an 8 times memory reduction. And again, here's the elegant bit. It happens at the same communication volume as ordinary data parallelism. You're now down to 1/8 of the footprint, and you still haven't paid a network penalty. For a lot of mid-sized training jobs, stage 2 is the sweet spot. Huge memory savings, no throughput hit. 8 times smaller sounds like it might be enough. But even at 1/8 the footprint, the raw model weights alone still crowd a single 24 gig card, and stage 2 never partitioned those weights. To actually land a 13B model on consumer hardware, you need the last stage. Stage 3 does the thing that sounds impossible. It partitions the parameters, the actual model weights, across your GPUs. No single card ever holds the whole model at once. When a layer needs its weights for a forward pass, DeepSpeed gathers just that layer's shards from the other cards on the fly, uses them, throws them away, and moves to the next layer. The memory reduction now scales linearly with how many GPUs you throw at it. 2 cards, you have again on top of everything. 64 cards, 64 times. The more you add, the thinner each slice gets. There's a real cost, and you should know it going in. Stage 3 raises your communication volume by about 50%, because now the parameters themselves have to be shuffled around on every pass. On cards linked by NVLink, that's fine. On 2 consumer GPUs talking over PCIe with no NVLink, that gather and scatter traffic can start to dominate your training time. The memory win is real. The throughput tax is also real. So here's the rig the title promised. 2 used RTX 3090s. That's 48 gigabytes of VRAM between them, and on the secondhand market, these have dropped to a few $100s a card. Pad the box out with cheap system RAM, and the whole build comes in under $1,000. With stage 3 on, the model weights split evenly across the 2 cards and drop into VRAM with room to spare. But the optimizer state is another matter. Even sharded, it's far too big to sit in graphics memory. That's where the last trick comes in. ZeRO-Offload takes that fat block of optimizer bookkeeping, which for a 13B model runs into the hundreds of gigabytes, and pushes it out of VRAM entirely, down into your regular system RAM. Your CPU holds it. The GPUs borrow slices back only when the optimizer step actually needs them. This is the piece the clean 13B on 2 3090s headline usually leaves out, and you need it to be true. You want a lot of system memory. Plan on 64 to 128 gigabytes of ordinary DDR RAM in the box. That's cheap next to VRAM, which is the whole point. You're trading expensive graphics memory for cheap motherboard memory.
DeepSpeed didn't stop there either.
ZeRO Infinity extends the same idea one level further down, spilling state past RAM and onto NVMe solid-state drives. That's how the same library gets used to fine-tune models with hundreds of billions of parameters. It's the backbone that trained Bloom at 176 billion and Microsoft's own giant models. The exact tool a solo builder runs on 2 cards is the tool LinkedIn's engineers disclosed running at production scale for their recommendation systems. Same library, different number of GPUs. There's a bandwidth catch worth naming plainly. Moving optimizer state between CPU and GPU rides the PCIe bus, which is dozens of times slower than the GPU's own memory. If the optimizer step lands on the critical path, that gap stalls you. DeepSpeed overlaps the transfers to hide most of it, and newer offload engines the team keeps shipping exist specifically to kill those stalls. But it's not magic, and on a 2-card PCIe rig, you will feel it. Now the part that surprises people. You'd expect wiring all this up to mean rewriting your training loop. It doesn't. DeepSpeed is a drop-in replacement for PyTorch's standard distributed training. You don't restructure your model. You don't rewrite the optimizer. You write a JSON config file that says which ZeRO stage you want and whether to offload. You swap your launch command, and that's the change. Hugging Face published the cleanest demonstration of this. Their engineers took a 3 billion parameter T5 model that dies with out of memory on a single 24 gig 3090 under plain PyTorch. They added a DeepSpeed config, changed nothing in the model code, and the run completed. Impossible to routine by editing a config file. So the honest verdict, should you do this? If you're chasing raw throughput per dollar, renting a single cloud A100 for a weekend often wins. The 2-card rig trains, but that 50% communication overhead and the PCIe offload tax mean it won't be fast. And for plenty of jobs, you don't need a full fine-tune at all. Parameter-efficient methods like LoRA sidestep the memory problem by only training a small adapter, and they're simpler to configure. But when you need a full fine-tune, every weight moving, which still beats adapters for hard, task-specific production work, and you want to own the hardware instead of renting it, this is the unlock. A 13 billion parameter model, learning on 2 graphics cards that cost less than a decent phone, because ZeRO refused to let a single one of them carry the whole load. The next question is just how far up you're willing to push it, because with NVMe in the mix, that ceiling sits a long way north of 13 billion.